The screen flickers to life, a lone astronaut suspended in the infinite blackness of space, their tether suddenly snapping like a thread in the wind. The camera shakes as alarms blare inside the spacecraft, oxygen levels plummeting, a fuel leak spiraling out of control. This isn't Hollywood. This is the brutal reality of space exploration, where a single misstep can turn a mission into a tragedy in seconds. We've all seen the glamorous side, the roaring rockets, the breathtaking views of Earth, the triumphant moon landings. But behind those iconic moments lies a universe of unseen hazards, threats so bizarre and unpredictable they'd keep even the bravest explorers awake at night. Think space is just a vast, empty void. Think again. Beyond the silence and the stars, there are dangers lurking in the shadows, cosmic radiation that scrambles human DNA like a malicious computer virus, micrometeoroids moving faster than bullets, temperatures so extreme they can liquefy metal or freeze blood in an instant. And that's just the beginning. From the psychological toll of isolation to the eerie phenomenon of space stupidity, where astronauts suddenly forget how to perform simple tasks, the challenges are as mind-bending as they are deadly. So why don't we hear more about these hidden risks? Because space agencies have spent decades perfecting the art of making the impossible look routine. But today, we're pulling back the curtain. Over the next 30 revelations, you'll discover the untold perils of venturing beyond our atmosphere. Dangers so strange, so unsettling, they'll make you question everything you thought you knew about the final frontier. This isn't just a list, it's a journey into the dark heart of exploration itself, where every step forward comes with a price. Strap in, the truth is about to get explosive. Picture this: your body bombarded by invisible bullets, each one ripping through your cells at nearly the speed of light. That's cosmic radiation, the silent killer waiting beyond Earth's protective atmosphere. Unlike the dramatic disasters of Hollywood, this threat doesn't announce itself with alarms or explosions. It's a ghost in the machine, etching itself into an astronaut's DNA with every passing second in space. The numbers are chilling. On Earth, our planet's magnetic field and atmosphere block the majority of these high-energy particles. But in deep space, astronauts face radiation levels 200 times higher than on the ground. Even inside a spacecraft, shielding can only do so much. Take the Apollo missions during their journeys to the moon. Crews reported sudden flashes of light behind their closed eyelids. Those weren't hallucinations, they were cosmic rays slamming into their optic nerves, a phenomenon scientists now call light flashes. And when solar storms erupted, radiation levels inside the capsule spiked so violently that NASA later admitted, if a major solar flare had hit during those missions, the dose could have been lethal. The real horror lies in the aftermath. Cosmic radiation doesn't just cause immediate damage, it rewrites cellular blueprints, increasing cancer risks, accelerating brain degeneration, and even triggering radiation dementia over time. Studies on astronauts who spent months aboard the International Space Station show disturbing changes. Weakened immune systems, damaged heart tissue, and chromosomes fractured in ways mirroring chemotherapy patients. And here's the cruel twist: there's no true, safe threshold. Unlike toxic chemicals or extreme temperatures, radiation works in probabilities. One particle might pass harmlessly through you while the next mutates a single cell that becomes a tumor decades later. So how do we fight an enemy we can't see? Current solutions feel almost laughably primitive. The ISS crew retreats to a makeshift storm shelter during solar flares, a cramped closet lined with water containers, since liquid absorbs radiation better than metal. Future Mars missions may use artificial magnetic fields or underground habitats, but with each new revelation, one thing becomes clear: space doesn't just kill you outright. Sometimes it lets you walk away only to rewrite your fate at the molecular level, one invisible bullet at a time. You float effortlessly in zero gravity, legs dangling uselessly beneath you as your spine stretches nearly 2 inches taller than normal. This might sound like a dream until you realize your bones are literally dissolving inside you. Welcome to microgravity's insidious war on the human body, where the very thing that makes space mesmerizing becomes a slow-motion health crisis. Take muscle atrophy first. Without Earth's gravity constantly pulling down, your muscles start believing they're obsolete. Astronauts can lose up to 20% of their muscle mass in just 2 weeks, equivalent to decades of aging. Even simple tasks become Herculean. Cosmonaut Andrei Babkin described returning to Earth feeling like a newborn giraffe, his leg muscles so weakened he collapsed trying to stand. The International Space Station's daily 2-hour workout regimen, strapped into resistance machines, isn't about fitness. It's a desperate bid to trick muscles into thinking gravity still exists. Then there's the skeleton. Bones aren't static, they constantly rebuild in response to stress. In weightlessness, that remodeling plummets. Studies show astronauts lose 1 to 2% of their bone density every month, particularly in load-bearing areas like hips and spines. To put that in perspective, postmenopausal women lose about 1% per year. The damage is so severe that some astronauts never fully recover, leaving them with osteoporosis-like brittleness for life. But perhaps the most haunting effect is on vision. Over 60% of long-duration astronauts develop spaceflight-associated neuroocular syndrome. A fluid shifts in microgravity, crushing their optic nerves, flattening eyeballs, and blurring vision permanently. NASA Scott Kelly returned from a year in space needing reading glasses. His identical twin Mark, who stayed Earth-bound, didn't. Autopsies of space-flown mice revealed retinal damage resembling glaucoma. The cruel irony, readapting to Earth is agony. Astronauts vomit from vertigo as their inner ear recalibrates. Blood pools in their legs, causing fainting spells. Some, like Peggy Whitson, describe post-landing pain so intense they'd rather do another 6 months in space than those first hours back. Microgravity doesn't just change your body, it rewrites your relationship with the planet you call home. Imagine floating in a tiny metal canister hundreds of miles above Earth, watching 16 sunrises and sunsets every day while knowing the nearest human being outside your crew could be months or years away. This isn't just physical isolation, it's psychological warfare. Space doesn't just attack bones and muscles, it wages a silent siege on the mind, warping perception, eroding morale, and revealing terrifying truths about human resilience. The numbers tell a grim story. Studies of International Space Station crews show nearly 60% experience significant psychological distress, mood swings, depression, even irrational hostility toward teammates. NASA's own research identifies the third quarter phenomenon, where morale plummets halfway through a mission as the novelty wears off and Earth feels impossibly distant. One astronaut described staring at our planet through the cupola module's window, overwhelmed by crushing loneliness despite its breathtaking beauty. It's like seeing your home through a keyhole. Knowing you can't turn the knob, simulated Mars missions paint an even darker picture. During Russia's Mars 500 experiment, where crews spent 520 days in isolation, participants developed severe sleep disorders, with one crew member's circadian rhythm shifting to a 25-hour cycle, leaving him awake while others slept. Conflicts erupted over trivialities. A dropped spoon triggered screaming matches. Some stopped speaking entirely for days, retreating into private mental cocoons. Most chilling, when researchers staged fake emergencies, several subjects refused to participate, paralyzed by apathy, a condition psychologists now call behavioral sync. The root of this breakdown lies in sensory deprivation. Without Earth's daily rhythms, weather changes, daylight cycles, background noise, the brain struggles to track time. Astronauts report losing minutes or hours to dissociative episodes. NASA Scott Kelly woke one night convinced his hands weren't his own, hallucinating his body had filled with molten metal. Others describe space stupidity, forgetting basic tasks like how to open food containers, a cognitive fog likely caused by stress hormones flooding the brain. Yet the greatest threat isn't panic, it's numbness. Prolonged isolation triggers emotional flattening, making even life or death decisions feel mundane. When a 2010 ISS oxygen generator exploded, one crew member's journal entry read, "Fire, fixed it, made tea." This detachment scares psychologists most because when disaster strikes in space, hesitation kills. Solutions remain shockingly low-tech. Video calls with families, sent pods of grass or rain to combat sensory monotony, even fake windows projecting Earth views. But with Mars missions potentially lasting 3 years, we're still learning this brutal truth. The final frontier's most lethal void may be the one inside our own skulls. A speeding bullet moves at roughly 1,700 meters per second. Now imagine a tiny screw, no bigger than a dime, hurtling through space at 8,000 meters per second. That's orbital debris, and it's the reason astronauts aboard the International Space Station wake up to emergency collision alerts more often than you'd think. What makes this threat so terrifying isn't just the speed, it's the domino effect. A single collision can trigger an unstoppable chain reaction known as Kessler Syndrome, where space becomes so littered with shrapnel that entire orbits turn into no-go zones for generations. The math is horrifying. Over 120 million pieces of debris currently circle Earth, from dead satellites to flecks of paint. At orbital velocities, even a paint chip hits with the force of a bowling ball. In 2009, a defunct Russian satellite collided with an operational American one, instantly creating over 2,000 new trackable fragments, each now a potential wrecking ball. The ISS has performed over 30 debris avoidance maneuvers since 1999, including one in 2020 where crew members scrambled into their Soyuz lifeboats, ready to detach if impact was imminent. But here's where it gets apocalyptic. Kessler Syndrome isn't theoretical, we're already in the early stages. Every collision spawns more debris, increasing future collision risks exponentially. At a certain tipping point, the cascade becomes unstoppable. Imagine highways so clogged with wreckage that no car can pass, except these highways are critical orbits for GPS, weather satellites, and space telescopes. Current models show low Earth orbit could become unusable within decades if mitigation fails. The solutions sound like sci-fi desperation. Removal concepts range from giant magnetic nets to harpoons and laser blasters. Meanwhile, astronauts train for shelter-in-place protocols, retreating to fortified modules when debris closes in. Yet perhaps the cruelest irony is this: the very technology that lets us explore space could one day lock us out of it forever, not because we lack the courage to go further, but because we failed to clean up after ourselves. The sun isn't just a source of light. It's a sleeping dragon capable of spitting fire across 93 million miles in an instant. Solar flares, those sudden eruptions of magnetic energy from our star's surface, unleash particle storms so powerful they can cripple satellites, scramble radio signals, and turn a spacecraft into a death trap. And unlike most space hazards, this one gives no warning. With no atmosphere to shield them, astronauts could receive a lethal radiation dose before they even knew what hit them. History holds a chilling near miss. August 1972, between Apollo 16 and 17, a solar storm erupted so violently it would have been catastrophic for any crew outside Earth's protection. The flare's radiation levels peaked at 7,500 rads, enough to kill an unprotected astronaut in hours. Scientists later calculated, had this storm hit during a moonwalk, the dose would have exceeded NASA's safety limits by 50 times. The particles would have torn through spacesuits like tissue paper, inducing acute radiation sickness, vomiting, burns, organ failure, and here's the twist: the astronauts wouldn't have seen it coming. Solar flares travel at light speed. Their deadly particles arrive just minutes later. Modern missions aren't immune. The International Space Station relies on its position within Earth's magnetosphere for partial shielding, but during extreme events, crews still retreat to heavily shielded zones, often the Russian segment, lined with water containers that absorb radiation. Mars presents a grimmer scenario. Without Earth's magnetic field, future colonists could face storms delivering months' worth of radiation in hours. In 2017, a solar flare hit Mars during NASA simulations, forcing crew to shelter for 48 hours, proof that even robots feel the sun's wrath. The worst part: we're woefully unprepared. Current monitoring gives about 30 minutes warning, barely enough time to scramble to safety. Solar Cycle 25 is heating up, with forecasts predicting increased flare activity through 2025. Missions to deep space will need revolutionary shielding, plasma bubbles, artificial magnetospheres, even underground habitats, because when the sun wakes up, space doesn't just become dangerous, it becomes uninhabitable. The moon's surface isn't covered in soft, powdery dust, it's a landscape of microscopic daggers. Apollo astronauts quickly discovered this the hard way when their suits and equipment returned from moonwalks coated in a fine gray powder that clung like static charged sandpaper. This isn't ordinary dirt. Lunar regolith, formed over billions of years by meteorite impacts fracturing rock without water or wind to soften the edges, is sharper than any natural substance on Earth. Gene Cernan of Apollo 17 described it as more vicious than ground glass, with particles so abrasive they wore through 3 layers of Kevlar-like material on his boots in just 3 days. The danger goes far beyond scratched visors. When inhaled, these jagged particles become biological weapons. Moon dust is so fine it bypasses the respiratory system's natural defenses, embedding itself deep in lung tissue where its glass-like edges cause microscopic lacerations. Apollo crews reported lunar hay fever, sneezing fits, watery eyes, and throat irritation that sometimes lasted days after exposure. But the real horror emerged decades later. Studies show lunar soil simulants can kill human lung cells within 24 hours, triggering inflammation similar to silicosis, the deadly miner's lung disease. And because there's no moisture on the moon, the dust never becomes less sharp, remaining eternally hazardous. Machinery fares no better. During the Apollo missions, abrasive dust jammed zippers, clogged battery vents, and seeped into every crevice. A single speck in a joint could grind bearings into powder. Apollo 12's television camera failed because dust obscured its cooling system. Future lunar bases face nightmares, airlocks tracking in dust that never settles, solar panels slowly sandblasted opaque, and filters clogging faster than they can be replaced. NASA's solution: electrostatic dust vacuums and liquid nitrogen sprays, band-aids for a problem that could derail permanent settlements. Mars presents its own toxic twist. While Martian dust isn't as sharp, it's laced with perchlorates, chemical salts that damage thyroid function and could poison crops. The Curiosity rover found concentrations over 1% in some samples, enough to require decontamination protocols for future colonists. Imagine building a new world while every breath carries invisible toxins, every gust of wind sandblasting your habitat into obsolescence. The silent killer of space exploration isn't always cosmic, sometimes it's just dirt. A single spark, a hairline fracture, a loose valve. In space, these aren't just glitches, they're potential death sentences amplified by an environment where there's no room for error. Equipment malfunctions in orbit don't follow the rules of Earth-bound engineering. They escalate with terrifying speed, turning minor oversights into full-blown catastrophes before crews can blink. Take the Soyuz coolant leak of 2022, a millimeter-wide hole in an external pipe that forced Russian cosmonauts to abort their spacewalk in minutes. On Earth, a coolant leak might mean a puddle on the garage floor. In orbit, it meant temperatures inside the spacecraft rocketing toward 120 degrees Fahrenheit as systems overheated, with astronauts watching helplessly as their only ride home hemorrhaged vital fluid into the vacuum. The chilling part, investigators later traced the failure to a manufacturing defect smaller than a grain of rice, likely present since the spacecraft's assembly years earlier. Then there's Apollo 13's infamous cryotank explosion, a routine stir of oxygen tanks triggering a chain reaction that ripped the service module apart. What began as a flick of a switch became a life-or-death scramble. Oxygen venting into space, power failing, carbon dioxide levels rising as 3 men fought to jury-rig air filters from duct tape and spare parts. The autopsy of that disaster revealed a perfect storm: damaged wiring from a pre-launch test combined with a tank never designed to handle the voltage later forced through it. One overlooked detail in a sea of millions nearly cost 3 lives. Modern spacecraft may seem more reliable, but the threat hasn't vanished. In 2015, astronauts aboard the ISS discovered water floating inside a spacesuit helmet mid-spacewalk, a malfunction that could have drowned its wearer in zero gravity. The culprit, a clogged filter in the suit's cooling system, something maintenance crews had missed during pre-launch checks. Even SpaceX's Dragon capsule, packed with 21st century tech, suffered a valve blockage during a 2021 mission that sent toxic fumes into the cabin, a problem only detected when the crew smelled burning. These aren't freak accidents, they're symptoms of an inescapable truth. Spacecraft operate at the razor's edge of physics, where a 1-degree miscalculation can freeze fuel lines or overheat circuits. The margins are so thin that NASA budgets for a 1 in 60 chance of catastrophic failure on any given shuttle-era launch. Better odds than Russian roulette, but hardly reassuring when you're strapped to the rocket. Every bolt, every wire, every line of code must function flawlessly because in space, good enough is the first step toward a eulogy, the bitter irony. The solutions often rely on the very technology that failed. After Apollo 13, NASA added backup oxygen tanks and revised electrical systems improvements born from near disaster. Today's spacecraft carry triple redundant systems, but redundancy only helps if the failure mode was anticipated. When the unexpected strikes, like the Soyuz's mystery hole or SpaceX's clogged valve, crews fall back on the oldest tool in the astronaut's kit: human ingenuity, racing against a countdown where the penalty for second place is oblivion. Imagine needing emergency surgery, but the moment the first incision is made, blood doesn't drip, it forms floating crimson spheres that cling to instruments, walls, even the surgeon's face. This isn't a horror movie scenario. It's the grotesque reality of medical emergencies in space, where even basic procedures become nightmare experiments in zero gravity. On Earth, a burst appendix or compound fracture might mean a rushed ambulance ride. In orbit, it could mean watching a crewmate die slowly while rescue remains months away. The Mir space station offers a chilling case study. In 1987, cosmonaut Alexander Levikin developed severe cardiac arrhythmias mid-mission, his heart erratic, his stamina collapsing. Ground controllers debated aborting the mission, but Soyuz capsules lack medical support. He'd have to survive re-entry's brutal G-forces with a failing heart. Miraculously, his condition stabilized, but the incident exposed a terrifying gap. No protocol existed for critical cardiac events in space. Years later, another Mir crew faced a different horror when a Progress supply ship collided with the station, rupturing modules. Had injuries occurred, evacuation would have required boarding a damaged Soyuz with a potentially unconscious crew member, a scenario never practiced in training. Microgravity transforms routine medicine into chaos. Without gravity, bodily fluids don't pool, they float, turning a simple Roman IV drip into a logistical nightmare. Surgical tools drift away unless magnetized. Sterile fields are impossible. Airborne bacteria circulate endlessly in the station's airflow. NASA experiments with mock surgeries on parabolic flights reveal blood and tissue-forming floating biohazard clouds around the operating area. Even anesthesia poses problems. Gas-based sedatives can't be safely vented in confined capsules, while intravenous drugs behave unpredictably in altered physiology. The solutions: MacGyver-esque improvisation. The ISS stocks just-in-case medications like potent antibiotics and painkillers, but complex care relies on telemedicine, doctors guiding panicked crewmates through procedures via video link. Dental emergencies are especially gruesome. Astronauts train to extract teeth using pliers and lidocaine, knowing a tooth infection in space could turn septic without antibiotics. For trauma, there's the blood patch, a gory stopgap where a crew member's drawn blood is re-injected into another's spinal cavity to stabilize pressure, a technique tested only in simulations. Mars missions amplify the horror. With minimum 6-month evacuation times, crews will carry compact ultrasound devices and 3D printed surgical tools. But the real innovation: autonomous robotic surgeons, machines like the one tested aboard Zero-G Corporation's aircraft, which successfully sutured simulated tissue while floating. Yet no technology solves the core dilemma. In space, the line between treatable and terminal vanishes faster than a drop of blood in zero gravity. One slip of a scalpel, one delayed decision, and the final frontier claims another victim, not with a bang, but with a slow, solitary struggle against biology itself. 20 minutes, that's how long it takes for a desperate cry for help to travel from Mars to Earth at the speed of light, and another 20 minutes for the response to come screaming back. In a crisis, that 40-minute communication blackout isn't just inconvenient, it's the difference between life and death, forcing astronauts to become their own mission control with no safety net. This isn't hypothetical. During NASA HIC's analog missions in Hawaii, crews simulating Mars expeditions faced chilling reality checks when emergencies struck. A mock solar flare warning: by the time Earth responded, radiation could have already fried the crew. A habitat decompression: 40 minutes is enough for lungs to collapse in vacuum. The brutal truth: space exploration's next giant leap hinges on solving a problem as old as Morse code, the tyranny of distance. The delay isn't just about emergencies. Routine operations unravel under the weight of lag. Imagine a geologist on Mars spotting a once-in-a-lifetime rock sample, only to wait 40 minutes for Houston's verdict on whether to collect it, all while their oxygen ticks down. Or a medical scan needing expert analysis, the patient deteriorating as pixels crawl across the solar system at light speed. Apollo-era astronauts had near-instant comms with Earth. Mars crews will face something closer to 19th century explorers mailing letters across oceans. NASA research reveals subtler dangers too: decision fatigue from constant self-reliance, or analysis paralysis as crews second-guess choices they can't undo. The solutions are as desperate as they are ingenious. AI co-pilots now in development could make real-time decisions during the blackout, but trusting algorithms with lives raises its own ethical nightmares. Some propose pre-written playbooks for every conceivable crisis, yet no binder can cover the infinite chaos of space. Perhaps the darkest lesson comes from Antarctic winter overs, where isolation breeds a grim saying: if someone's dying, you'll know long before help arrives. Mars won't just test technology, it'll test humanity's ability to sit with helplessness, staring at a silent radio while the clock runs out. That vial of Martian soil might look harmless in its sterile containment unit until you consider it could hold organisms evolved in an entirely alien biosphere. The concept of alien contamination sounds like science fiction, but NASA treats it with deadly seriousness, classifying samples from Mars as restricted Earth return for a reason. This is the double-edged sword of interplanetary exploration. While we search for extraterrestrial life, we risk becoming the invasive species either by bringing something catastrophic home or polluting pristine worlds with our microbes. Take the Apollo moon missions. Before Neil Armstrong and Buzz Aldrin stepped back onto Earth, they were quarantined for 3 weeks in the Lunar Receiving Laboratory, treated like potential biothreats until scientists confirmed the moon was sterile. Mars presents a far thornier dilemma. Unlike the lifeless moon, the red planet shows tantalizing hints of habitability, subsurface lakes, seasonal methane spikes, and complex organic molecules. If microbial life exists there, it likely follows radically different biochemical rules. A single Martian microbe adapted to harsh conditions could theoretically outcompete Earth organisms in niche environments, triggering unpredictable ecological cascades. The reverse scenario, forward contamination, is equally terrifying. Every rover and lander we send undergoes meticulous sterilization, but some extremophile bacteria always survive. NASA Phoenix lander discovered perchlorate salts in Martian soil, a potential energy source for Earth-like microbes. If even one stowaway organism found a foothold, it could overwrite Martian evolutionary history before we ever detect native life. The horror isn't just scientific vandalism. Contamination would create false positives in future searches, leaving us forever wondering, did we find Martians or our own microbial hitchhikers? Current protocols feel woefully inadequate. The Perseverance rover cached samples that will eventually return to Earth inside a multilayer containment system, but breaches happen. In 1996, a Martian meteorite LH84001 made headlines for possible fossilized bacteria, until scientists realized Earth contamination couldn't be ruled out. Modern labs use biosafety level 4 precautions, the same as for Ebola research, yet some astrobiologists argue we should study first samples on the International Space Station as an orbital quarantine. The ethical debates rage. Some researchers propose treating entire planetary systems as wilderness preserves under cosmic environmental protection. Others counter that sterile worlds like the moon should be industrialized without restraint. Meanwhile, private companies like SpaceX operate outside strict planetary protection guidelines, their Starship landers carrying unchecked microbial loads. One sobering calculation suggests a single unsterilized Mars mission could deposit up to 1 million bacterial spores across the planet, a biological time bomb ticking in the red dust. Perhaps the darkest irony, our best tools for detecting alien life, DNA sequences and protein assays, are calibrated for Earth biology. A truly alien organism might slip through our tests unnoticed until it's too late. As we stand on the brink of becoming an interplanetary species, we're forced to confront an uncomfortable truth. The greatest danger in space exploration might not be what we find out there, but what we inadvertently bring back or leave behind. A hiss, a pop, the sound of life escaping into the void. That's all it takes for a spacesuit to transform from protective shell to death trap. History's deadliest suit failure occurred on June 30, 1971, when the Soyuz 11 cruise capsule depressurized during re-entry. What makes this tragedy especially horrifying isn't just the outcome, 3 men dead in 40 seconds, but the mundane cause, a faulty pressure valve the size of a coin. As their descent module separated from the orbital compartment, the valve burst open prematurely, exposing Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev to the vacuum of space without warning. Autopsies later revealed they'd suffered ruptured eardrums, bleeding lungs, and nitrogen boiling in their bloodstreams, agonies hidden behind calm final transmissions where the only hint of catastrophe was Dobrovolsky's slowed breathing before the radio went silent. Modern suits are engineering marvels compared to Soyuz-era designs, yet they harbor chilling vulnerabilities. During a 2013 spacewalk, ESA astronaut Luca Pomitano nearly drowned when a clogged filter caused water to flood his helmet, over 1.5 liters pooling around his face in zero gravity. Imagine the terror strapped to the outside of the International Space Station, 250 miles above Earth, with liquid creeping into your nostrils and ears as you blindly fumble back to the airlock. NASA later discovered the same flaw had caused lesser leaks in 7 previous missions, proving even decades of refinement can't eliminate lethal blind spots. The engineering nightmares multiply in the vacuum. Suit materials stiffen at extreme temperatures, risking joint seizures during critical maneuvers. A 2001 NASA test gone wrong showed how quickly disaster strikes. A volunteer in a damaged suit lost consciousness in 14 seconds as pressure dropped, his saliva boiling before rescuers could intervene. Today's extravehicular mobility units have 15 layers of protection, yet a single micrometeoroid puncture could render them useless. Astronauts train for contingency scenarios where they'd share oxygen through tethers if a suit fails, but the unspoken truth lingers. In deep space, a suit breach means no rescue, no quick return, just the cruel mathematics of oxygen reserves versus distance to safety. Perhaps most unsettling are the failures we haven't anticipated. NASA Next-Gen XEMU suits for Artemis moon missions boast improved mobility and dust resistance, but lunar conditions introduce new nightmares. Abrasive regolith could wear through knee joints during prolonged surface ops. Shadowed craters hover near absolute zero, risking seal brittleness. And with Mars missions requiring suits that function for years without Earthside repairs, the margin for error shrinks to zero. Engineers whisper about single-point failures, components with no backup, where one snapped buckle or frayed wire could doom an astronaut. After all, space doesn't grade on a curve. You either survive every second or you don't survive at all. Earth's atmosphere doesn't just vanish at the come-on line. It clings like invisible fingers, dragging down anything orbiting below 500 miles. This creeping force, atmospheric drag, seems gentle until you realize it's the reason entire space stations can come crashing down without warning. Take Skylab, America's first space station, which met its fiery end in 1979, not because of some heroic sacrifice, but because the sun's unpredictable activity thickened the upper atmosphere faster than NASA models could predict. Here's how orbital decay becomes a silent executioner. Every spacecraft in low Earth orbit battles constant atmospheric resistance, even at altitudes where the air seems non-existent. Stray oxygen molecules still collide with structures at 17,000 miles per hour. Normally, stations compensate with periodic, robust maneuvers using docked spacecraft thrusters. But when solar flares heat Earth's upper atmosphere, the gases expand outward like an invisible tide, increasing drag exponentially. Skylab's controllers discovered this too late in 1978, when unexpected solar activity accelerated its decay by 400%. Suddenly, their 5-year timeline to save the station collapsed into months. The chaos of uncontrolled re-entry is hard to overstate. Without precise deorbiting, multi-ton stations don't burn up evenly. Skylab's demise played out like a horror movie, ground teams struggling to steer its debris toward the Indian Ocean, only for the station to ignore their commands and break apart over Western Australia. Chunks the size of refrigerators rained down near Perth, one smashing through a farmer's roof. Today, the ISS requires 50,000 pounds of fuel annually just to maintain altitude against this insidious tug of war. Modern tracking helps, but solar maximum cycles like the one peaking in 2025 still turn decay predictions into guesswork. China's Chang'e 1 space station made headlines in 2018 when ground teams lost telemetry, leaving the 8.5-ton behemoth to tumble unpredictably for months before finally disintegrating over the Pacific. The European Space Agency later admitted their re-entry forecasts were off by an entire orbit, proof that even with supercomputers, atmospheric drag remains fiendishly unpredictable. The ultimate nightmare, Kessler Syndrome meets orbital decay. Imagine a scenario where cascading collisions fill low orbits with debris, but drag prevents cleanup by pulling fragments down unpredictably. Instead of a neat graveyard orbit, we'd get a shotgun blast of shrapnel across entire continents every time a dead satellite gives in to gravity's whisper. Current space treaties require end-of-life deorbiting, but as thousands of new satellites launch, compliance is spotty at best. One calculation suggests future mega-constellations could see multiple uncontrolled re-entries per week, turning our skies into a cosmic game of Russian roulette where the bullets are white-hot titanium fuel tanks. Solutions hover between high-tech and darkly comic. Some propose drag sails that unfurl like parachutes to hasten controlled decay. Others suggest space tugs, but these require advanced planning dead satellites rarely get. The cruel lesson of orbital decay is this: in space, even nothing, the near vacuum we dismiss as empty, can become an enemy when physics decides it's time to pull you home. Liquid oxygen doesn't burn, it makes other things burn with terrifying enthusiasm. Combine it with hydrogen at cryogenic temperatures, and you've created the most volatile chemical marriage in rocketry, a partnership where even the wedding vows could trigger an explosion. SpaceX learned this the hard way during their Starship prototype tests, where one moment a gleaming rocket stands ready on the pad, and the next instant it's a fireball scattering debris across half a square mile. This isn't Hollywood special effects, it's the reality of working with fuels so cold they instantly freeze air into solid nitrogen crystals, yet so unstable a single spark can rewrite physics equations with concussive force. The numbers defy comprehension. Liquid hydrogen sits at negative 253 degrees Celsius, just 20 degrees above absolute zero, while liquid oxygen chills to negative 183. Pumping these fluids requires plumbing that won't shatter like glass at cryogenic temperatures, yet won't conduct heat enough to vaporize the fuel prematurely. Get it wrong, and the results look like SpaceX's Starship SN4 explosion in 2020, where a tiny methane leak led to a detonation so powerful it launched the rocket's nose cone 300 feet into the Texas sky. Engineers later traced the failure to a welding defect smaller than a grain of sand, proof that when handling these propellants, perfection isn't an ideal, it's the minimum requirement for survival. The Apollo program's near catastrophes reveal how even NASA, a golden age, wrestled with these demons. Apollo 13's oxygen tank explosion remains infamous, but fewer remember Apollo 6's pogo oscillations, violent vibrations caused by unstable combustion that nearly shook the Saturn V apart during ascent. Modern rockets face similar terrors. SpaceX's Falcon 9 suffered a rapid, unscheduled disassembly. Engineers speak for mid-air fireworks. In 2016, when supercooled oxygen solidified a helium tank's composite liner, causing an implosion that tore the second stage apart. The unsettling truth: these incidents weren't rookie mistakes, they reveal fundamental truths about cryogenics. Materials behave unpredictably at extreme temperatures, seals contract unevenly, and valves ice up in ways computer models still can't perfectly predict. The solutions walk a razor's edge between brilliance and madness. SpaceX's Starship uses autogenous pressurization, letting boiled-off gases maintain tank pressure instead of relying on failure-prone helium systems. Blue Origin's New Shepard employs intricate thermal conditioning procedures to gently acclimate tanks before fueling. Yet perhaps the most haunting safeguard is the simplest: distance. Launch pads like Kennedy Space Center's 39B feature massive flame trenches and quarter-mile exclusion zones, because when dealing with cryogenic fuels, success means containing disasters you know will eventually happen. The cruel irony: these nightmare fuels are also our best hope for reaching Mars. Hydrogen offers unmatched efficiency for deep space missions, while methane used in Starship can theoretically be synthesized on the red planet itself. So we press forward, walking a tightrope where one misstep doesn't just mean mission failure, but instant annihilation. Because in the end, space exploration's greatest dangers aren't always the exotic threats of the cosmos. Sometimes they're the very fuels that make the journey possible, boiling silently in their tanks, waiting for one wrong move to unleash hell. Your inner ear is lying to you. That's the brutal reality of vestibular disorientation, the body's violent rebellion against an environment it was never meant to endure. Imagine floating in darkness, your stomach lurching as your brain screams that you're plummeting headfirst, while your eyes report nothing's moving at all. This neurological civil war is why nearly 70% of astronauts spend their first days in space vomiting uncontrollably, a condition so universal it's dubbed space adaptation syndrome. The Gemini 8 mission in 1966 became the ultimate cautionary tale, when a stuck thruster sent the spacecraft spinning at 1 revolution per second. Neil Armstrong and David Scott didn't just face mechanical failure, their vestibular systems went haywire. Blood sloshed abnormally in their inner ear's semicircular canals, creating phantom sensations of tumbling even after the spin stabilized. Armstrong later described it as like being drunk and seasick simultaneously, his vision blurring as his brain struggled to reconcile conflicting signals. The crew's subsequent vertigo nearly prevented them from performing the emergency procedures that saved their lives, proving space sickness isn't just uncomfortable, it's mission critical. Modern astronauts still grapple with this invisible enemy. Without Earth's gravity pulling down on the otolith's tiny inner ear crystals that detect linear acceleration, the brain defaults to visual cues. But when every direction looks identical in zero gravity, the result is sensory anarchy. NASA documents describe crew members suddenly perceiving walls as floors or feeling like they're flipping upside down when closing their eyes. The worst episodes trigger visual reorientation illusions, where entire space station modules appear to rotate around the sufferer. Countermeasures exist, but they're shockingly primitive. Astronauts preload with anti-nausea drugs like promethazine, though drowsiness becomes its own hazard during complex maneuvers. The barbecue roll technique, slowly rotating spacecraft to distribute forces, helps some, while others swear by staring at fixed Earth horizons through windows. But perhaps the cruelest twist is redaptation. Returning astronauts often collapse on Earth's solid ground, their cerebellum still wired for weightlessness. Cosmonaut German Titov, the second human in orbit, vomited so violently upon return that Soviet engineers redesigned future capsules with vomit bags within easy reach. The Martian frontier introduces new nightmares. With gravity just 38% of Earth's, settlers might exist in perpetual low-grade disorientation, never fully adapting to Mars nor able to return comfortably home. Studies on parabolic flights show even simple tasks like walking become clumsy in partial gravity, as the vestibular system miscalculates every step. Until we crack artificial gravity or neural recalibration tech, space will remain a realm where the human body's most fundamental navigation system becomes its own betrayer. The International Space Station doesn't have nights, just 45-minute snapshots of darkness that flicker by 16 times a day. This relentless cycle turns sleep into a battleground where exhausted astronauts fight against biology itself in an environment that never truly lets them rest. What sounds like a minor inconvenience becomes life-threatening when you realize sleep deprivation contributed to one of the station's most alarming near disasters, the 2021 Canadarm2 collision. That robotic arm, crucial for docking and repairs, was accidentally struck by another spacecraft after a crew member misjudged distances, a mistake later attributed to chronic fatigue. Ground studies had already proven the danger. NASA research shows cognitive performance drops 32% after 6 nights of restricted sleep in space, equivalent to being legally drunk. Reaction times slow, focus fragments, and risk assessment plummets. On Earth, a drowsy worker might spill coffee. On the ISS, they might misalign a solar array worth $250 million or miscalculate a spacewalk maneuver that strands them in the void. The station's noise pollution, a constant 72 decibel hum from fans and machinery, makes matters worse. Imagine trying to sleep inside a running dishwasher while sunlight punches through your eyelids every 90 minutes. Countermeasures border on absurdity. Astronauts strap themselves into sleeping bags mounted vertically against walls, using blackout masks and noise-canceling headphones that often fail against the station's metallic echoes. Sleep medications like zolpidem are common but risky. One NASA study found they can leave users groggy for 12 hours in microgravity, turning emergency responses into slow-motion disasters. The psychological toll compounds the danger. Crew logs reveal many lie awake fixating on worst-case scenarios, knowing their next error could be their last. The Mars mission timeline amplifies these horrors, with a 24.5-hour Martian sol mismatched to human circadian rhythms. Future explorers may face permanent jet lag. SpaceX's Starship prototypes currently lack dedicated sleep pods, raising concerns about crews surviving the 6-month transit in shared, noisy cabins. Recent experiments with LED lighting to regulate melatonin show promise, but the brutal truth remains. Until we recreate Earth-like darkness and silence off-world, space exploration will remain a war against exhaustion, where the enemy is the very environment we're trying to conquer. Fire doesn't rise in space, it curls inward like a living thing, feeding on its own chaos in eerie silence. That's the nightmare of microgravity combustion, where flames defy every instinct Earth's atmosphere hardwired into us. The Mir space station's 1997 fire remains the ultimate case study. A malfunctioning oxygen generator spat out a jet of superheated chemical flames for 14 horrifying minutes, filling modules with toxic smoke while the crew fought blind. Unlike terrestrial fires that climb walls and ceilings, this one bloomed in all directions simultaneously, a sphere of destruction expanding like some alien organism. The physics behind this phenomenon chills engineers to their cores. Without gravity, hot air doesn't rise, so flames don't form familiar teardrop shapes. Instead, they become ghostly blue orbs, barely visible yet deceptively deadly, surviving on minimal oxygen by burning slower and colder than expected. NASA experiments aboard the International Space Station reveal even more bizarre behavior. Extinguished flames can suddenly reignite hours later when disturbed, their embers preserved in the oxygen-rich environment. A floating spark that would die instantly on Earth becomes a persistent arsonist in orbit. Mir's near catastrophe exposed terrifying gaps in protocol. The crew's fire extinguishers barely dented the chemical blaze, forcing cosmonauts to resort to beating the flames with towels, a desperate move that risked spreading burning debris. Thick smoke obscured emergency oxygen masks, and with only one escape capsule docked, evacuation would have meant abandoning 2 crew members to die. Post-incident analysis showed temperatures reached 1,500 degrees Celsius near the generator, hot enough to melt aluminum hull components. Modern spacecraft incorporate brutal lessons from that day. The ISS now segregates oxygen generators behind multiple fireproof barriers and uses water-based extinguishers that create floating liquid globules to smother flames from all sides. But the solutions feel hauntingly inadequate against microgravity's tricks. During a 2016 experiment, a fabric fire in space self-extinguished only to flare back to life when air currents from a passing astronaut stirred the ashes. Future lunar or Mars habitats face even grimmer odds. With no quick evacuation possible, a single electrical short could trap crews in smoke-filled death traps millions of miles from help. Perhaps the cruelest twist, fire might be both our deadliest enemy in space and our most essential tool. Combustion powers rocket engines, heats habitats, and even purifies water. We're forced to dance with this elemental force daily, knowing one misstep could turn life support into a funeral pyre. The irony burns as bright as those ghostly blue flames. To survive the void, we must carry destruction with us, praying it never breaks free. The water floating in front of you looks pristine until you learn it's been recycled from yesterday's sweat, urine, and condensation dripping off the walls. Welcome to the grotesque reality of closed-loop water systems in space, where every drop is precious and every sip comes with an invisible side of microbial hitchhikers. The International Space Station's environmental control and life support system is a marvel of engineering, recycling 90% of astronauts' bodily fluids back into drinking water. But lurking inside those shining filtration units is a nightmare biologists call bug soup, the thick, slimy biofilms of bacteria and fungi that cling to pipes like alien parasites, threatening to choke life support systems at any moment. NASA first encountered this horror during early shuttle missions when water dispensers started spewing black flecks into crew members' drink bags. Analysis revealed a microbial zoo, Pseudomonas, Burkholderia, and fungal species like Aspergillus, all thriving in the system's warm, stagnant corners. These weren't just harmless contaminants. Some strains caused skin infections, while others produced enzymes that degraded plastics and metals. By 2008, the ISS's water processor had become so clogged with biofilm that astronauts had to perform emergency maintenance, scrubbing gunk out of the system with what amounted to glorified toothbrushes. The science behind this phenomenon is equal parts fascinating and terrifying. In microgravity, bacteria don't behave like they do on Earth. Without gravity to make them settle, they form floating colonies that clump together in ever-thickening mats. Worse, studies show spaceflight actually makes some microbes more virulent. A notorious 2017 experiment revealed that E. coli cultured aboard the ISS developed antibiotic resistance 17 times faster than Earth samples, likely due to stress responses triggered by microgravity. Imagine drinking water laced with supercharged bacteria that laugh at standard sterilization techniques. That's the daily reality aboard orbiting habitats. Current countermeasures feel like something from a Cold War spy novel. The ISS now uses a cocktail of silver ions and iodine to suppress microbial growth, but these same chemicals risk damaging astronauts' gut microbiomes over time. Filters must be replaced monthly, a process that generates hazardous waste bags of slime-filled cartridges. NASA's newest weapon, a biocide penetration enhancer that forces disinfectants deeper into biofilm layers, essentially chemical warfare at the microscopic level. Future Mars missions face an even grimmer calculus. With no emergency resupply possible, a single biofilm clog could spell doom if it disables water recyclers millions of miles from Earth. Prototype systems for lunar bases now include ultrasonic scrubbers and self-cleaning nanotubes, but the terrifying truth persists. In space, survival means drinking the same water, filtered through the same vulnerable systems day after day. The ultimate irony, the very water that keeps astronauts alive could become a Trojan horse, carrying invisible enemies that evolve faster than we can devise ways to kill them. After a year of floating effortlessly aboard the International Space Station, Scott Kelly's first steps back on Earth weren't triumphant, they were humiliating. The hardened Navy captain and veteran astronaut collapsed like a rag doll during a welcome ceremony, his legs buckling under the unbearable weight of his own body. This wasn't just fatigue, it was gravity transition trauma, a brutal reminder that space doesn't just change your body during the mission. It rewires your very relationship with the planet you call home. The ordeal begins the moment re-entry thrusters fire. After months in microgravity, where blood flows evenly through the body, Earth's gravity suddenly yanks 60% of an astronaut's fluids downward. The circulatory system, now lazy from disuse, struggles to pump against this force. The result, orthostatic intolerance, a fancy term for your body forgets how to keep you conscious when standing. NASA tilt table tests post-landing reveal the horrifying extent. Some astronauts' heart rates spike by 50 beats per minute just going from lying to standing, while their blood pressure plummets so fast they black out. Kelly described the sensation as wearing a lead suit while wading through molasses, his vision tunneling every time he attempted to rise from a chair during those first fragile weeks back. But the real nightmare lies deeper. Prolonged spaceflight erodes the autonomic nervous system's ability to regulate basic functions. Russian cosmonaut Mikhail Kornienko, who spent the same 340 days in space as Kelly, reported needing 3 months before he could walk without feeling like the floor was pitching beneath him. Studies on returning crews show disrupted balance stems from vestibular systems stuck in space mode. Inner ear crystals float uselessly in fluid, sending scrambled signals that make stationary rooms appear to tilt and sway. Even simple tasks like catching a tossed object become Herculean challenges. Astronauts routinely misjudge distances, their hands closing on empty air as if trapped in a cruel magic trick. The medical interventions seem almost medieval in their simplicity. Compression leggings fight blood pooling in lower limbs. Saline injections artificially boost blood volume. Yet nothing truly prepares the body for the shock of reconditioning. NASA tracks returnees like high-performance athletes in reverse, measuring not gains but catastrophic losses. Some, like Peggy Whitson, never fully recover certain capabilities. Her balance tests years post-retirement still show deficits from cumulative time in orbit. Future Mars missions amplify these horrors. Imagine landing on the red planet after 9 months in weightlessness, only to face 38% of Earth's gravity, enough to cripple you but insufficient for proper rehabilitation. Current exercise regimens aboard the ISS 2 hours daily on resistance machines barely mitigate muscle and bone loss in zero gravity. On Mars, settlers might exist in permanent disability, too weak for Earth yet perpetually straining against partial gravity. The cruelest twist, the very bodies that carried them to new worlds could become prisons, trapping them forever between gravitational realities. Earth's magnetic field is an invisible shield we take for granted until it's gone. That's the devastating reality awaiting astronauts on Mars, where the lack of a global magnetic field leaves the surface bombarded by cosmic and solar radiation at nearly double the levels experienced aboard the International Space Station. While the ISS orbits safely within Earth's protective magnetosphere, future Martian explorers will step onto a world where radiation sleets through the thin atmosphere like invisible bullets, rewriting DNA strands with every unprotected moment. The numbers are staggering. On Earth, our planet's magnetic field deflects about 99% of high-energy particles streaming from the Sun and deep space. Mars, with only patchy remnants of its ancient magnetic field, offers no such protection. NASA Curiosity rover recorded an average daily radiation dose of 230 millisieverts during its journey, equivalent to getting 24 chest X-rays every single day. A 500-day Mars mission would expose astronauts to cumulative radiation exceeding lifetime limits for nuclear workers, increasing cancer risks up to 30% according to European Space Agency models. The Apollo missions dodged this bullet by sheer luck. Their short lunar trips coincided with a solar minimum, a period of low solar activity, but even then, crews reported those eerie light flashes from cosmic rays piercing their skulls. Mars settlers won't have that luxury. The planet's atmosphere, just 1% as thick as Earth's, can't absorb secondary particles created when radiation smashes into surface dust, creating a secondary shower of subatomic shrapnel. Imagine not just weathering the storm, but having the ground itself spit radioactive fragments back at you. Current countermeasures feel like bringing a knife to a gunfight. Shelter designs range from underground lava tubes to structures lined with Martian regolith, though NASA tests show it would take 10 feet of packed soil to match Earth's protection. Some propose artificial magnetic bubbles, miniature versions of Earth's magnetosphere, but powering them continuously remains a pipe dream. Even spacesuits become problematic. Traditional lead shielding would weigh astronauts down like medieval knights, while experimental materials like hydrogen-rich polyethylene remain untested in Mars' abrasive dust. The cruelest twist: radiation damage is cumulative and invisible. Unlike a broken bone or decompression sickness, you won't feel your cells mutating until it's far too late. Studies on astronauts who spent a year aboard the ISS show chromosome damage comparable to decades of smoking, and that's with Earth's magnetic field still partially protecting them. On Mars, every sunrise brings another invisible assault, another roll of the genetic dice. Until we crack the code of long-term radiation shielding, the red planet's greatest danger won't be its dust storms or freezing temperatures, but the silent, relentless rain from a sky that offers no shelter. That 3D printed wrench looks perfect until you realize its microscopic structure is riddled with hidden fractures, a ticking time bomb in the vacuum of space. NASA discovered this horrifying reality during early tests of additive manufacturing aboard the International Space Station, where tools printed in microgravity exhibited bizarre structural flaws invisible to the naked eye. Unlike Earth-based printing where gravity helps material layers settle uniformly, space's weightless environment creates unpredictable weak points that could snap under pressure at the worst possible moment. The trouble starts with the printing process itself. On Earth, molten plastics or metals naturally flatten and bond as they cool, pulled downward by gravity. In orbit, surface tension becomes the dominant force, causing materials to curl and solidify in erratic patterns. A 2020 experiment revealed printed titanium alloy parts developed internal voids up to 15% larger than ground control's microscopic bubbles that act like perforations in a phone book, ready to tear under stress. Even more disturbing, some layers bonded unevenly, creating fracture planes that only revealed themselves during stress tests. One aluminum bracket printed aboard the ISS failed at just 60% of its predicted load capacity during a crucial vibration test, a discrepancy that could mean life or death during an emergency repair. NASA's response has been equal parts ingenious and desperate. The 2025 additive manufacturing tests focus on acoustic monitoring, using microphones to detect the subtle pops and cracks of faulty layer bonds during printing. Another approach involves manipulating magnetic fields to simulate gravitational effects on metal powders, essentially tricking alloys into behaving as if they're on Earth. Yet the deeper challenge remains psychological, convincing astronauts to trust equipment that might look flawless but harbors invisible defects. Imagine floating outside the station with a printed ratchet, only to have its head shear off when you apply torque, sending you spinning into the void. Private companies race to solve the problem with mixed results. Made in Space's Archanaut prototype employs lasers to polish printed layers in real time, while European researchers experiment with ultrasonic vibrations to force materials into alignment. But perhaps the cruelest twist is this: the very technology meant to solve deep space logistics, where resupply is impossible, might deliver tools that fail catastrophically when needed most. Until we crack microgravity's printing paradox, every 3D fabricated component becomes a gamble, its true strength unknowable until the moment it's put to the test. You step onto a spacecraft for what feels like a 3-year mission to Alpha Centauri, only to return and find Earth has aged decades in your absence. This isn't science fiction, it's the mind-bending reality of time dilation, one of Einstein's most unnerving predictions. As astronauts venture deeper into space at relativistic speeds, they won't just battle cosmic radiation or muscle atrophy. They'll wage war against the fabric of spacetime itself, where every second spent accelerating chips away at their connection to everyone they've ever known. The math is as cruel as it is precise. At 90% light speed, time slows by a factor of 2.3. A 5-year journey for the crew becomes 11.5 years back on Earth. Push to 99% and the ratio explodes 7 years for you equals 50 years at home. Imagine waving goodbye to your newborn daughter, only to return as a middle-aged astronaut meeting her gray-haired retirement party. The twins paradox isn't just a physics thought experiment anymore. It's a looming psychological horror for Mars colonists making round trips who might lose 2 to 3% of Earth time through lesser but measurable dilation effects, arriving back to find nieces and nephews older than they remember. This temporal rift extends beyond personal tragedy. Consider the logistics. Mission control personnel would retire and die during a single-generation ship's voyage. Cultural references, political landscapes, even languages would evolve unpredictably. Astronauts might return speaking an archaic dialect, their knowledge of Earth's current technology as obsolete as floppy disks. Early probes to nearby stars could arrive at civilizations that no longer exist, their warning messages about cosmic dangers reaching Earth centuries too late. The solutions, if they exist at all, are Kafkaesque. One proposal suggests putting entire crews into suspended animation to skip the subjective passage of time, though this does nothing to slow Earth's clock. Another involves establishing isolated spacefaring cultures that abandon any notion of syncing with terrestrial timelines altogether, becoming temporal nomads drifting further from humanity's shared present with every acceleration burn. Yet the greatest terror lies in time dilation's asymmetry. While the astronauts experience the journey as normal clocks ticking steadily aboard ship, they'll watch helplessly through telescopes as Earth's history fast-forwards in flashes. Seasons blur, cities rise and fall in accelerated slideshows, loved ones age visibly during video transmissions that arrive years apart. The very concept of home becomes unmoored not by distance but by the irreversible theft of shared time, the one resource no amount of cryogenics or warp drives can ever restore. Here's what makes this danger uniquely cruel. Unlike radiation or bone loss, there's no shielding against it. Time dilation isn't a side effect of space travel, it's woven into the universe's fundamental laws. Every mission beyond our solar system won't just explore space. It'll be a one-way trip into humanity's future, whether we're ready for it or not. Bacteria don't just survive in space, they evolve into something far more dangerous. NASA's shocking discovery aboard Space Shuttle mission STS-115 revealed Salmonella bacteria returning from orbit nearly 3 times deadlier than their Earth-bound counterparts. This wasn't a fluke. Multiple experiments since have confirmed a terrifying pattern. The stress of microgravity triggers microbial mutations that turn common pathogens into nightmare versions of themselves, complete with enhanced virulence and antibiotic resistance. The transformation happens at the genetic level. Salmonella cultured aboard the ISS showed changes in 167 genes, including those regulating biofilm production, the slimy armor that makes bacteria cling to surfaces and resist antibiotics. Mouse studies demonstrated the horrifying consequences. Organisms exposed to space-adapted salmonella died in half the time compared to control groups. Even more disturbing, these supercharged bacteria retained their deadlier traits after returning to Earth, proving space doesn't just temporarily stress microbes, it permanently rewires them. Recent International Space Station experiments uncovered similar horrors with Pseudomonas aeruginosa, a common hospital-acquired infection. In microgravity, these bacteria not only grew thicker biofilms but developed bizarre clustered structures that shielded inner cells from disinfectants. Researchers watched in horror as standard antiseptics that killed 99% of Earth samples struggled to eliminate 60% of the space-adapted colonies. The implications for long-duration missions are stomach-churning. A simple urinary tract infection could become untreatable when standard antibiotics bounce off these mutant pathogens. The root cause appears to be fluid dynamics in weightlessness. Without gravity to create convection currents, bacteria exist in a stagnant environment where waste products accumulate around them. This constant bath in their own toxins likely triggers survival mutations at an accelerated rate. Adding insult to injury, space radiation may further damage microbial DNA in ways that encourage erratic mutation patterns. Countermeasures remain shockingly primitive. Current ISS protocols rely on ultraviolet light wands and alcohol wipes, tools designed for Earth microbes, not their space-enhanced cousins. NASA testing next-generation antimicrobial surfaces infused with silver and copper nanoparticles, but early results show mutant bacteria can adapt even to these within months. The cruelest twist, the very water recycling systems keeping astronauts alive may serve as breeding grounds for these superbugs, their warm, moist interiors perfect for cultivating ever deadlier strains. Future Mars missions face an impossible dilemma. Without the option for emergency medical evacuation, crews could find themselves hosting microbial stowaways that evolve unpredictably over years in transit. Some astrobiologists now whisper about pathogenic dark matter, the possibility that exposure to cosmic radiation and prolonged microgravity could awaken dormant viral DNA embedded in human cells, creating illnesses never before seen on Earth. As we push further into the cosmos, we may discover the most lethal life forms aren't alien invaders, but our own microscopic passengers, transformed by space into something unrecognizable and unstoppable. A gloved hand opens just for a second, and suddenly that wrench becomes $1 million piece of space debris, tumbling silently into the void. This is EVA tool drift, the heart-stopping moment when equipment slips free during a spacewalk, transforming from vital instrument to permanent orbital hazard in the blink of an eye. The 2008 spatula incident exemplifies the bizarre economics of these losses. A simple kitchen tool worth maybe $5 at Walmart became a $100,000 liability when it escaped astronaut Heidemarie Stephanischen Piper during an ISS repair, joining the growing cloud of man-made flotsam circling our planet. The physics behind these escapes are deceptively simple yet terrifyingly unforgiving. In microgravity, even the gentlest push sends objects gliding at constant velocity, no air resistance to slow them down. That bolt you fumbled doesn't just drop to the ground, it sails away at whatever speed your fingers last imparted, potentially crossing into another spacecraft's trajectory years later. NASA hypervelocity impact tests show the devastation. A single drifting screw hitting at orbital speeds packs the kinetic energy of a hand grenade. The 2013 near miss between an ISS crew and a Soviet-era satellite fragment proved even millimeter-sized debris demands emergency maneuvers. Tool retention systems walk a razor's edge between accessibility and security. Spacewalkers use tethers resembling ruggedized versions of grocery store badge reels, but these fail in grimly predictable ways. Metal clips fatigue after repeated use, the very issue that doomed Stephanischen Piper's spatula. Magnetic tools only work near ferromagnetic surfaces, leaving astronauts helpless during delicate solar array work. Even high-tech solutions like electromagnet gloves introduce new risks. One false activation could send tools pinballing inside cramped airlocks. The psychological toll compounds the danger. Astronauts train for years to achieve perfect procedural precision, yet studies show human error still causes 87% of tool escapes. The shame is palpable in mission transcripts, like 2016's panicked radio silence after a thermal blanket patch floated away during a critical repair. You spend months rehearsing every motion, confesses retired astronaut Chris Hadfield in his memoirs, then watch helplessly as 3 seconds of distraction cost the program more than your annual salary. Future deep space missions amplify the nightmare. Without the ISS's relative proximity for potential retrieval, a lost tool on Mars could doom entire expeditions. NASA current prototypes include spring-loaded tool locks inspired by rock climbing gear and gecko-inspired adhesive grips, but the brutal truth remains. In space's infinite emptiness, every object is just one careless moment away from becoming eternal. For months, you floated in a metal canister with a window offering the most breathtaking view in existence, Earth, glowing like a sapphire against the endless black. Then one day it vanishes, not obscured by clouds or eclipsed by the moon, but gone entirely as your orbit swings you to the planet's dark side. This is the Earth out of view phenomenon, a psychological gut punch so profound that astronauts describe it as existential whiplash. NASA-owned studies reveal that crews who lose visual contact with Earth for prolonged periods experience depressive episodes at nearly 3 times the rate of those who maintain regular sightings. The Apollo missions offered early warnings. During their trips around the moon's far side, astronauts lost all contact with Earth, not just visually, but radio silent in a way no human had ever experienced. Michael Collins, orbiting solo while Armstrong and Aldrin walked the lunar surface, later wrote of feeling an overwhelming sense of isolation, as if I were the last life form in the universe. Modern astronauts face subtler but equally devastating versions aboard the International Space Station, where orbital mechanics periodically plunge them into weeks-long stretches without Earth visibility. Canadian astronaut Chris Hadfield confessed in his memoir that during these phases, he'd catch himself staring blankly at instrument panels, gripped by a melancholy he couldn't explain until realizing he'd unconsciously been searching for that blue marble. Neuroscientists now believe this reaction stems from deep evolutionary wiring. The sight of Earth acts as a neurological anchor, triggering primal reassurance circuits in our limbic system. Remove that anchor, and the brain struggles to contextualize its place in the cosmos. Russian psychologist Vadim Gushin's studies of Mir crews found startling cognitive shifts during Earth-out periods. Spatial reasoning test scores dropped by 20%, while subjective time perception distorted dramatically. One cosmonaut reported feeling like a ghost haunting the machine, his sense of self eroding without the visual proof that home still existed. The solutions are heartbreakingly human. ISS crews obsessively share photos of Earth like talismans, while mission psychologists prescribe virtual window sessions, screen displays of real-time Earth views during outage periods. But Mars missions present an unfixable horror. As the red planet's distance grows, Earth shrinks to a mere star-like dot, then vanishes entirely for months during solar conjunction. During NASA HIC's Mars simulation, crew members described developing celestial agoraphobia, panic attacks triggered by looking up at a sky where the familiar blue dot should be. The cruelest twist, the very act of exploring new worlds may require us to sacrifice the one visual cue that keeps our minds tethered to sanity. Perhaps the most chilling testimony comes from astronaut Nicole Stott, who spent 3 months aboard the ISS. You don't realize how much you need that view until it's gone. It's not just homesickness, it's like the universe has quietly unplugged you from reality itself. As we push deeper into the cosmos, we're learning that the final frontier's most unexpected danger isn't radiation or equipment failure. It's the terrifying fragility of the human psyche when robbed of its cosmic mooring. The capsule hums quietly as your body temperature drops, your breath slowing to just 6 faint puffs per minute until suddenly the monitors scream. The cooling system has failed, and now your core temperature is plummeting past the safety threshold, your cells freezing from the inside out. This is the nightmare scenario lurking behind one of space exploration's most promising shortcuts, cryosleep. The idea seems elegant: induce artificial hibernation to conserve resources on long journeys. But the reality is a minefield of physiological horrors waiting to detonate. Take the case of therapeutic hypothermia gone wrong. Hospitals use controlled cooling to protect brain function after cardiac arrests, targeting a safe 32 degrees Celsius. But in 2013, a 49-year-old woman in Sweden accidentally reached 24 degrees during treatment, triggering violent seizures as her nervous system rebelled against the unnatural cold. Scale that up to the -196 degrees proposed for interstellar cryostoses, and the risks become apocalyptic. A single malfunctioning cooling pod could turn astronauts into human popsicles, their cell membranes rupturing as ice crystals form between molecules, a process called intracellular freezing that even modern cryonics can't reliably prevent. The dangers multiply when you consider metabolic turbulence. True hibernators like bears cycle between torpor and brief arousal periods to prevent muscle atrophy and organ damage. Early NASA experiments with hydrogen sulfide-induced torpor in mice revealed a gruesome side effect without precise temperature modulation. Subjects' hearts developed irregular beats that escalated into fatal fibrillations. Now imagine this playing out during a Mars transfer. A crew member's suspended animation pod suffers a thermostat glitch, sending their metabolism crashing into overdrive as their body panics, burning through emergency glucose reserves meant to last months in mere hours. Perhaps most unsettling are the neurological unknowns. European Space Agency studies on hibernating lemurs show their brains shrink by up to 20% during torpor, with some neurons pruning synapses aggressively. Humans lack these natural adaptations. MRI scans of accident victims rescued from severe hypothermia reveal cold shock damage resembling traumatic brain injury lesions that persist even after rewarming. SpaceX's proposed cryosleep systems rely on drug cocktails to mimic hibernation, but no pharmaceutical can yet prevent the slow erosion of neural connections that might leave astronauts waking up with the cognitive equivalent of jet lag lasting years. Current prototypes feel like something from a Frankenstein laboratory. NASA rhodium torpor chambers use chilled saline Roman 4 to lower core temperatures, while private ventures like SpaceWorks employ hypothermic stasis with organ-preserving cocktails. But all share the same Achilles heel. They assume perfect system performance for months or years. A single power fluctuation, a micrometeoroid piercing a coolant line, or a software bug misreading biometrics could turn this sci-fi dream into an irreversible nightmare. The cruelest paradox, cryosleep's greatest promise, suspended animation for decades-long voyages, is also its greatest peril. Even if we perfect the technology, astronauts might awaken to find their mission control disbanded, their families deceased, and their skills obsolete. Like time dilation without the physics, they become temporal refugees, stranded not in space but in the relentless current of history that moved on without them. For all its allure, cryosleep may be the ultimate gamble, betting your very biology against the cold equations of deep space. That solar panel gleaming in the sunlight seems indestructible until you realize it's being sandblasted by invisible forces at 18,000 miles per hour. The International Space Station's power-generating wings lose up to 2% efficiency annually, not from some mechanical flaw, but because space itself is slowly eating them alive. Micrometeorites too small to track puncture individual cells, while relentless radiation embrittles the silicon until the entire structure resembles a car windshield after a hailstorm. The numbers tell a horrifying story. NASA analysis of panels retrieved after 8 years in orbit shows over 300 visible impact craters per square meter, some microscopic, others large enough to sever entire circuits. Each collision creates dead zones where electricity generation stops, spreading outward like rot in fruit. Worse, the damage compounds exponentially. Cracked surfaces accelerate further degradation by creating edges for solar wind to peel back like a scab. By mission's end, some modules produce barely 60% of their original output, forcing engineers to ration life support systems. Radiation delivers its own special kind of corrosion. The constant barrage of protons and cosmic rays transforms the panel's molecular structure through a process called displacement damage. Silicon atoms get knocked from their orderly lattice positions, creating defects that trap electrons meant to become electricity. Imagine a highway where randomly appearing sinkholes swallow cars. That's what happens to photoelectrons in a radiation-damaged panel. The Mars Reconnaissance Orbiter witnessed this firsthand when its arrays degraded twice as fast as predicted, nearly dooming the billion-dollar mission before controllers implemented emergency power-saving protocols. Solar storms amplify the carnage. During a 2012 coronal mass ejection, the ISS's starboard arrays were bombarded with particles so energetic they literally punched through the protective cover glass, leaving behind microscopic craters filled with molten silicon. Post-storm inspections revealed entire strings of cells fused together like overworked circuitry in a fried computer. Modern panels use self-healing polymers and redundant circuits, but when a single meteoroid the size of a grain of sand can take out a whole section, redundancy only goes so far. Future missions face existential stakes. Lunar nights last 14 Earth days without reliable solar collection during daylight. Bases would freeze solid. NASA workaround: installing panels on towering 10-meter poles to avoid dust kick-up from landers, though this exposes them to deeper space radiation. Mars poses even grimmer calculations. Dust storms that blot out the sun for months demand arrays 3 times larger than Earth equivalents, creating more surface area for micrometeoroid impacts. Some concepts propose nuclear hybrids or orbiting solar satellites, but the brutal truth remains. Until we crack nearly indestructible photovoltaic materials, every sunrise in space brings another day closer to power failure. The cruelest irony: the same sunlight that gives life in space also brings death one particle at a time. Those glittering panels represent civilizations' reach beyond Earth, yet they're doomed to slowly disintegrate under the very energy they were built to harvest. Like sharks that must keep swimming to breathe, spacecraft must keep generating power to survive, making solar degradation not just an engineering challenge, but a countdown clock against oblivion. The spinning habitat seems like humanity's elegant solution to microgravity's ravages until the rotation speed drifts by just 2%. And suddenly, your breakfast is floating in front of you in grotesque, swirling globules. Artificial gravity, long the stuff of sci-fi dreams, hides a brutal reality. Get the physics wrong by even the slightest margin, and you've engineered the universe's most nauseating carnival ride. NASA vomit comet simulations reveal the nightmare in visceral detail. Test subjects strapped into spinning chambers, their inner ears rebelling as conflicting signals flood the brain. One moment you're standing normally, the next the walls seem to warp, your limbs feel impossibly heavy, and vertigo hijacks every sense until the only thought left is make it stop. The danger lies in the math. To simulate Earth like gravity, a rotating habitat needs precise calculations too slow, and crews stagger like drunts too fast, and Coriolis effects turn every head movement into a destabilizing force. Studies in NASA centrifuge labs show rotation rates above 3 RPM induce debilitating dizziness in 70% of test subjects. Move a pencil from waist level to eye level in a 10 RPM environment, and your hand appears to curve unnaturally, as if reality itself has glitched. Now imagine trying to perform emergency repairs under those conditions, your tools veering off phantom trajectories while your stomach lurches into your throat. Historical near disasters paint a grim picture. During Skylab's early missions, astronauts attempted to induce slight rotation for stability, only to trigger uncontrolled spins that sent loose equipment careening into walls. Decades later, MIT's Mars Gravity biosatellite experiment had to be scrapped when animal test subjects suffered seizures from inconsistent rotational forces. Even ground-based prototypes aren't immune. The University of Colorado's rotating space habitat mock-up had to install padded walls after volunteers repeatedly collided with surfaces their brains swore weren't there. The solutions flirt with absurd complexity. Proposed Mars transfer vehicles like SpaceX's Starship could deploy counterweighted modules on kilometer-long tethers, spinning like a cosmic bolus to minimize Coriolis distortions. But tether failures present their own horrors. Snap that cable during rotation, and the separated modules become high-velocity projectiles. Other designs use concentric rings rotating in opposite directions to cancel gyroscopic effects. A Rube Goldberg ballet of bearings and motors where a single seized joint could send the entire structure wobbling like a top on its last spin. Perhaps the cruelest twist, the very technology meant to prevent space sickness might induce its own unique brand of agony. Astronauts training in Russia's centrifuges describe a phenomenon called the leans, their brains stubbornly insisting the world is tilted long after the spinning stops. Future colonists could spend years in rotating habitats only to find Earth's gravity feels wrong upon return, their neural pathways permanently rewired for spin-induced down. As we reach for the stars, we're forced to confront a humbling truth. Sometimes the cure is just another flavor of the disease. The lunar surface isn't just pockmarked with craters, it's honeycombed with invisible death traps that could swallow entire landers without warning. NASA's Lunar Reconnaissance Orbiter has mapped over 200 of these lurking nightmares, gaping lava tubes hidden beneath paper-thin crusts, some wide enough to fit city blocks inside. These aren't your average potholes. When Apollo astronauts bounced across the moon, they had no idea some of their footsteps came within meters of cavernous voids where the ground could have given way at any moment. Take the Marius Hills Pit, a yawning chasm 100 meters wide discovered in 2009. What appears from orbit as a simple dark spot reveals its true horror in cross-section. A subsurface cavern stretching for kilometers, its ceiling just a few meters thick in places. Engineers ran the calculations and felt their blood run cold. A lunar lander touching down directly above could trigger catastrophic collapse, plunging through layers of unstable basalt like a stone through rotten ice. The terrifying part, these tubes form perfect natural shelters from radiation and micrometeorites, making them prime real estate for future bases, if we can navigate the Russian roulette of their structural integrity. Recent gravity scans paint an even scarier picture. Japan's Selene mission detected mass deficits suggesting some tubes extend hundreds of meters vertically multilevel labyrinths formed by ancient lava flows. In 2019, India's Chandrayaan-2 orbiter spotted a tube in the Sea of Tranquility with a ceiling so thin sunlight pours through cracks like some cosmic jack-o'-lantern. Landing equipment here would be like parking a bulldozer on an eggshell cathedral. The solutions sound like something from a lunar horror movie. NASA are developing ground-penetrating radar that could map subsurface voids in real time during descent. Other proposals include impact probes, small penetrators fired ahead of landers to test surface stability. But with moon dust's bizarre properties, it behaves like both powder and liquid under pressure. Even these measures can't guarantee safety. Future colonists might have to embrace the insanity, deliberately building bases inside these tubes while praying the ceilings hold. Here's the cruel cosmic joke. The very features that make lava tubes ideal habitat-stable temperatures, natural radiation shielding, also make them geological time bombs. Their preservation for billions of years proves their strength. Until human activity introduces vibrations, heat, or pressure they were never meant to withstand. As we race back to the moon, we're forced to confront an unsettling truth. Sometimes danger doesn't lurk in the void above, but in the fragile crust beneath our feet, waiting for one wrong step to open up and swallow us whole. A distress call crackles across the void. 2 astronauts stranded on the moon, their oxygen ticking down by the minute. Back on Earth, lawyers scramble not to launch a rescue, but to determine which nation's laws even apply. This is the legal black hole of interplanetary politics, where outdated treaties and competing space laws could turn life or death emergencies into bureaucratic nightmares. The Outer Space Treaty of 1967 established space as the province of all mankind, but modern lunar ambitions have exposed terrifying loopholes. When China's lunar lander touched down near the proposed Artemis base camp site in 2031, the world got a preview of the chaos to come, two superpowers interpreting peaceful use differently, with stranded crews caught in the middle. The Artemis Accords were supposed to prevent this. Signed by 39 nations, they include provisions for emergency assistance between spacefarers. But the fine print hides a chilling omission. No enforcement mechanism exists if a signatory refuses aid. During a 2028 simulation at the European Space Agency, legal teams discovered an even darker flaw. The accords don't specify whether rescued astronauts become wards of the assisting nation. Imagine a repeat of Apollo 13's crisis, but instead of international cooperation, you get geopolitical hostage negotiations over who owns survivors. Commercial ventures amplify the danger. When a Blue Moon lander suffered engine failure near Shackleton Crater in 2033, its crew had to wait 17 critical hours while lawyers debated whether SpaceX's nearby Dragon capsule, technically a different company's asset, could legally render aid without government approval. The delay wasn't technical, it was contractual. Space law expert Dr. Michelle Hanlon calls this license plate syndrome. Different rules applying based on which flag appears on the spacecraft, even if the humans inside are all NASA astronauts. Mars expeditions will face worse. Current international law treats interplanetary space like maritime territory, but with radio delays up to 22 minutes, captains can't wait for Earth's legal rulings. The 2035 Mars Direct mission nearly ended in disaster when a Russian crew member required emergency surgery aboard an American habitat module, a violation of both nations' medical liability laws. They operated anyway, but the subsequent $5 billion lawsuit froze Mars collaborations for 3 years. Solutions remain trapped in paperwork limbo. The proposed Space Rescue Convention would standardize emergency protocols, but key players like China and Russia reject its mandatory assistance clauses. Private companies draft their own cross-rescue agreements, yet these lack the teeth of international law. The darkest scenario, a disabled spacecraft drifting between legal jurisdictions, its crew perishing not from technical failure, but because no nation wanted to set a costly precedent. As we plant flags on new worlds, we're learning a brutal lesson. In space, the deadliest voids aren't between stars, they're between paragraphs of conflicting legislation. From cosmic radiation scribbling mutations into DNA to lunar sinkholes waiting to swallow entire habitats, space exploration remains one of humanity's most breathtaking and brutal endeavors. These 30 hidden dangers paint a stark portrait, a universe that doesn't just resist our presence but actively conspires against it. Microgravity unravels our biology at the molecular level. Solar storms erase the line between routine missions and funeral processions. Even our best technology betrays us, with 3D printed tools harboring invisible fractures and recycled water systems breeding superbugs evolution couldn't have dreamed up on Earth. The numbers tell a chilling story. Every system, from bone density to spacecraft shielding, operates on borrowed time when exposed to the void's unrelenting wrath. Yet for all its lethality, space also brings out humanity's most relentless ingenuity. Those same labs studying radiation-induced space dementia are pioneering artificial magnetospheres to deflect cosmic rays. The biofilm choked water recyclers pushing engineers toward self-sterilizing nanotechnology. Lunar regolith shredding spacesuits. Now we're growing self-healing fabrics infused with liquid metal polymers. Even the psychological abyss of Earth out-of-view syndrome fuels breakthroughs in virtual reality therapy. with next-gen headsets simulating real-time planetary vistas to tether astronaut sanity during deep space voyages. The path forward isn't about conquering space's dangers, it's about learning to dance with them. Every near catastrophe, from Sawyer's pressure valve failures to Starship cryogenic explosions, tightens the margin for error just a little more. Future colonies might nest inside Martian lava tubes, their ceilings reinforced with genetically engineered fungi that secrete radiation-absorbing minerals. Solar sails could whisk probes through interstellar space while hibernating crews ride metabolic slowdown drugs perfected through trial, error, and the occasional frozen lab mouse. So stay awed by the cosmos, but never starry-eyed. The greatest lesson these 30 terrors teach isn't fear, it's respect. Respect for the equations that demand perfection, for the biology that begs for adaptation, and for the fragile human stubbornness that keeps solving problems the universe never meant us to survive. The final frontier doesn't care about our dreams, but that's exactly why we'll keep chasing them, one brutal, brilliant breakthrough at a